Hey class, it's just me, Mr. Wee, with physics. Physics teacher, all right? I'm here to go over the last chapter for this month. It's gonna be chapter 7 in your physics book. It's on momentum. Okay. Let me move some stuff around. Welcome to class, right? This is an example of momentum. I'm gonna say it's where momentum is conserved, right? Um, you don't really need to know momentum to understand, like, hey, look, like this ball is going here, hits these three marbles, and then the other marble comes up, comes back down, hits these three marbles. You understand that something's being conserved. Well, we call that momentum. So what is momentum? Okay. I'm just going to describe it. It's just the momentum of a ball depends on mass and velocity. So if you remember last time, force, if I can force, we talked about a force. Today we're talking about momentum. Force was equal to mass times acceleration. Okay? It depended on those two things. Today we're talking about momentum, and it's going to talk about mass times velocity, which is a little bit different. And it's actually really hard to describe the difference between the two. So we're going to briefly go over like how you should kind of view it and see it. So let me move this out the way. Okay, so again, the momentum of something, of a ball or whatever, depends on its mass and its velocity. Okay, so in this case, you have a mass of 1 kilogram, and for ball A, and a velocity of 1 meters per second. It's traveling that fast. Its momentum total will not be as strong as marble B or ball B, which has the same exact mass of 1 kilogram, but it's traveling slightly faster, as indicated by this arrow or this vector arrow. Okay, and then overall, you can kind of see whose momentum is a little bit higher, even though they both have the same mass. Okay, so one way of looking at momentum is you can think of it as an object's unstoppability. Okay, like its amount of unstoppability. You ever hear something that's like, oh my god, that car like that carries so much momentum, or like that guy has so much momentum in his punches, or I don't know if you guys have that as a conversation on a regular daily basis. Man, punches are more momentous today, um, sometimes you hear it as a metaphor, like a movement has a lot of momentum going. Okay, it's like really hard to stop the momentum of like a social movement or something. Okay, um, but the physical science base of it is it's a measure of something's an object's mass and its velocity put together. So in, I know it's kind of weird, but you would want to say momentum's m, but it's not, because m belongs to something else. Lowercase m belongs to mass. Okay, so p is what denotes momentum. So if I can go back to my example over here, here momentum is denoted as p, and then mass is just m times velocity. And so it's p equals mev. And if you remember force is actually means F equals ma. Okay, it's one of the most fundamental things that you'll learn in physics. But in momentum, it's not quite as looked at as quite as foundational, but it is. It is actually as important as force. But we do actually talk about a little force quite a bit more. Okay. So momentum, so the units basically, P is equal to, we would have something that's in kilograms. We convert things to kilograms. And then the velocity is, we always talk about meters per second. I mean, velocity, you can talk about kilometers per second, kilometers per hour. Mass could be just grams or milligrams. But when we're talking about momentum, calculating things for momentum, we compare things by converting everything towards kilograms, and everything in speed being in meters per second. So it's, the unit for this was kilograms times meters per second. Up here, force, if you remember, was kilograms. Again, for any time that there's mass, it's meters per second squared, which gives you kilograms meters per second squared. Like if I said I had 2 kilograms per meter squared, that'd be the equivalent of saying 2 newtons. Okay, this, I don't really have anything today. It would just be like is equal to 2 kilograms meters per second, and that's it. That's actually all you have. You don't say that that's newtons. That's not. This is different from kilograms times meters per second squared. Meters per, like with that fractional line, get it? Meters per second squared is equal to like a newton. Okay, like 2 kilograms per meter, or meters per second squared, is equal to 2 newtons. This is not equivalent to newtons. It's just 2 kilograms meters times meters per second. So that's just units. That's just stuff to like talk about units and stuff like that. Just remember momentum is equal to m times v. Okay, so again, what are the differences? So force is equal to ma, F is force, m is equal to the mass of the object, a is acceleration. So we know that, but what like is the meaning behind it? And I want you to think about that. Like, I don't know. It just looks like a formula to me. And physics can kind of become that way, where it just becomes a string of formulas they have to remember. And it can be easy or hard depending on who you are, okay? But at a conceptual level, this is what I want you to think about. Force is an external action on a body that either shifts the body or does not. Momentum is the amount of motion in a moving body that instigates the movement, okay? So if I could bring this, so check it out. Force, this person right here, this is the object we're looking at right here. Or you have to ask, what's the object in this scenario that's being moved or not moved? It's this thing, okay? This is like a bale of hay or something like that. I have no idea. I think it's a bale of hay. And it's a person that's trying to push it. He's applying the force onto an object. We're going to measure if that, or we're going to see if that thing actually moves or not, if this person put enough force into that object. Well, in this case, the object is different. We're like, in this case, I think the object over here would be something that's already in motion. So over here, the person was in motion here, but we weren't focused on him. He wasn't our object. The object was whatever force he was putting into. So the object was this guy receiving a force, okay? This, however, you should look at momentum as something that's like, this is the object, and we're actually looking at how much momentum it gives. Does that make sense? So force is typically what we think of like things that come in. We take a force, okay, or forces come at us. Where momentum is like coming from us. Like how much momentum are we giving out? Like the like the metaphor is like the social revolution. It came with a lot of momentum. We were talking about the actual social revolution or the social whatever, so social movement has momentum, right? We're talking about the object itself is providing momentum, okay? But forces, we talk about how much we like take forces, okay, or how much like force we're receiving from something else, okay? So it's the amount of motion in a moving body that instigates the movement. Okay. So we're actually almost done, but there's some calculations that might take a little bit more time. In terms of concept, this is pretty much like the last thing I'm going to go over. Whoa. This is pretty much the last thing that I'm going to go over in terms of a new concept. And then after that, I'm going to have to go into detail with like some formulas and some problems, okay? It's the conservation of mass? No, it's the conservation of momentum, okay? As it says on the screen right there, okay? What does that mean? It means whatever your total momentum was before is going to equal the total momentum after. So what do we got? We got m times v, that's the equation for momentum, of an object A, okay? Plus, if you talk about momentum of another object, like in a scenario, like object A touches object B, the momentum they both carried in, like m times v is the momentum. So the momentum of whatever object A brought in, plus the momentum of object B, however much that had, at the very end, after they collide or they touch, they have to interact. Okay, that's the whole point. You can't, or else this formula would be never ending. You don't know how many different objects are involved in each scenario. You're looking at something like an interaction between like two or more different objects or something, or actually you could just talk about one. But we're talking about typically like things interacting. So it's like two or more. So we're looking at object A interacting with object B, and then however, whatever momentum they carried into their scenario before, once they collide or touch or something, we measure their momentums after, it should equal the same thing. Okay, so what do I mean by object A, object B? So for instance, let's do a scenario where object A goes in with a momentum, it has a mass, and it has a velocity, it's going in, okay? And like object B wasn't quite going as fast, but hey, it's like this is object B, okay? Its velocity was not going quite as fast, but in its mass, I don't know, was probably a little bit different. I don't really know, okay? But if you, what I'm saying is, let's say if we let's just take an easy number like 2 and 3, okay? Mass over here was like 3. and I'll just say 1, okay? Its velocity, or its momentum here, or sorry, PC, I already messed it up. Momentum of A is equal to mass of A times the velocity of A, and the velocity of B over here was its mass, or mass of B, sorry. This should be capital. I should keep it consistent. I'm sorry. It's kind of confusing. Plus, or times its velocity. Okay, and they're about to collide. So this is like their momentums before. Okay, and let's say they actually hit. Let's say they actually like at the moment they hit. That's what like their velocities and masses are. Okay, so let's do a calculation. That's like I'm not putting any units yet, so it'd be 2 times 3, and that's 6. And this over here would be mass is 3 times 1. That'd be 3. Okay, so before scenario and after scenario. So let's say before we actually measured their PA, the first object. So this is before. I'm gonna draw an after. Okay, so this is before, like right before they touched. Okay, before object A has this momentum, and I calculate that's 6. PA is equal to all that is equal to 6. So I'm gonna put that in here, and then let's say over here PB, get it? Peanut butter, okay, right? 6 plus 3. 6 plus 3. The total momentum that they both have, like right before like the moment where they hit, or like at the moment where they hit, is like 9. Okay, 9. It's kilograms meters per second technically. That means over here, the result or the result on this side, not the fact that you put equals means that whatever's on this side is 9 has to be the same on this side. This has to equal 9. Okay, does that make sense? So, but we haven't discussed what's going on here yet. But this is the base thing is momentum before has to be equal to the momentum after, but it could change for each object. Does that make sense? So the total momentum of both of those guys has to be the same at the end. But look what happens. Okay, so let's go back to my example really quick. So let's make the after scene. Okay, this is the after scene. So let's say now object A, okay, let's say that its mass is now, it's still 2, right? Its mass never changed. But let's say its velocity is 0. Like it completely stopped. Like, I don't know, it completely stopped like in place. And after it hit B, it like B shot forward and A just didn't move at all. Okay, so let's look at B. B was a little bit bigger, but it's totally moving super fast now. Mass is 3, and then let's say actually, and let's say I don't know what the new let's say what I don't know the new velocity. Okay, so let's go back and plug in some stuff up here now. All right, so let's say that before I had PA before, oh, and this is after. I'm sorry, I should have said that. So like I'll say on the left hand side is the before, and this is the after. Okay, let me grab like some whiteout really quick. And you know, it's kind of confusing to say PA and PA. Let's put PA like to make it like the after. Let's make like a little apostrophe in the corner. I don't even know if I'm saying that right. My English is really bad. You get it? My English is really bad because I don't know what the heck that's called. Is that a comma? Is that a quotation? I don't know. Okay. And let's put an apostrophe over here. So like, or they call that prime. I'm actually not making that up. That's actually in physics. That signal is called prime. So it indicates to you the momentum of A before, and then with the prime thing or whatever, it says momentum after. Okay, does that make sense? Okay, so if I want to calculate the P of A after, it'd be its mass times its new velocity, which would be 2 times, oh, crud, 0. What is the overall momentum of this guy? And like this guy's super going fast, okay? Like after they collided, like let's say they and it just stays still, and the other guy went forward. Okay, I should have drawn that, but I didn't draw that. Okay, its overall momentum, even though it has a mass, its overall momentum, because it's not just mass, it's mass and its velocity. 2 times 0 is 0. So its overall momentum is 0. So up here, the p prime would now be 0. So what does that mean for PB? Peanut butter prime, actually. Okay, what is PB going to be then? So let's look. It has to match the left-hand side. The left-hand side before was PA had a momentum of 6, PB had a momentum of 3, total is 9. The other side has to be a total of 9, but we just solved for the new momentum of PA, which is 0. What does that mean PB has to be then? Just by logical deduction, this has to be 9, okay? The momentum of B has to be 9. And we can use that to our advantage. PB, because remember, we actually don't know the velocity. That's going to help us out. PB is equal to mass of, and I guess I'll even do the mass like primes too, like the mass of the A after the collision and the velocity after the collision. So that should be denoted with the apostrophes. Same with this one, mass of B, sorry, and I should keep it capital A, keep it very consistent. The notation, that's capital A. I'm kind of butchering this up. Mass of B after and the V of B after. Mass we know is 3, and I don't know what v of b prime is, but you know what I do know? I don't know the velocity that I got afterwards, but what I do know is up here, just from logical deduction, this is 9, and this has to be 9, and we calculated the momentum to be 0 here. The momentum of b has to be 9, so that way 0 plus 9 is equal to 9. So PB has to be 9. And we can use that to our advantage to solve VB. So let's divide both sides by 3. And then 9 divided by 3 is 3. So the velocity of B has to be 3. So we just did some problem solving. So hopefully that kind of helped you out there. But that's basically the gist of this guy. Okay. So you can rewind that if you want to see an example or see how that works. But this is what I just gave you examples of what all this stuff means. MA and MV actually, if you notice, don't have a prime there, like after. Well, in case you're wondering, does the mass actually change? Like, look at the mass of A versus like mass of, like, did that mass, which is right here, which is 2, mass of A 2, did that ever change? Does that mass of that ball change? No, the mass of, even like a car before and after a crash, its mass is roughly the same. Even if you lose some parts in the air and whatnot, it's roughly the same. So that's why they're like, this MA doesn't require that apostrophe because the mass never changes. But anyways, that's not super important, so don't worry about it if that confuses you, okay? But just know that the primes mean like what the velocities were after, and then just know that MA, you could put the apostrophe in the corners up here if you want. You're not wrong. You won't be wrong in saying that, but you don't have to because the masses don't change. Okay, so let me give you another example, okay? Visual example. So this is hard to see, but there's a ball that's moving, or I think it's actually like a pin or something, like a flat pin or flat little button. Okay, yeah, it's definitely not a pin. I don't know what I was saying. Its mass is 10, I guess, and its velocity is 6. How do I know? Because if you look at the up here, it's kind of badly color coordinated, but I think velocity is like a lighter green or blue. So velocity has an arrow too, and we know velocity is speed with a direction. Mass has no direction. Mass doesn't need a direction to be mass, okay? So the mass of this button is 10, and its velocity is 6 going in this direction. Look at this guy. This guy has a mass of 15 because he's obviously bigger than that button, but he has no velocity. He's just sitting still. So check this out. How are we going to set that up? We're going to calculate the momentum of this guy, which is 10 times 6, it's mass times velocity, and the mass of this guy 15, but there's a velocity of 0, it's just 15 times 0. Let's see what that's going to equal. Actually, we don't know yet. I'll just leave it like that. In our heads, that's 15 times 0, that's just 0, plus 10 times, that's a total of 60 on this side, so keep that in mind. Let's look at what happens when they collide. So when they collide, Whoosh, okay? This guy is completely stopped. How do I know? There's no velocity. So it might not say velocity equals 0, v equals 0, but that's kind of tricky. They're saying that, oh, you should be smart enough to know that if I don't put in velocity, v is equal to 0, and I don't draw an arrow, then obviously there's no velocity. You you puking bigger. I don't know. Okay. All right. Sorry about that. Very horrible accent and whatnot. Yeah, accent imitation. Okay. So the mass though is 10. Still, the mass doesn't change. Remember what I said. Okay. But the velocity is now changed. It's 0 for this guy. So again, there's another problem. We have a new velocity for the blue button. It might not be 6, but it has to be something. So check out where my arrow is pointing. Okay. Um, the button here is 15. What's its new velocity? But we know this button has a velocity. So what are the new values going to be on the right hand side? The after, the momentum's after. So the momentum of this guy is 10 times 0. Okay, it's going to be 0. And then it's 15 times this mysterious velocity, which we don't know. So we'll just put 15 times v. Okay, no a, no va, no vb. Okay, just make it simple. All right. So as I said before, when we do the math on the left hand side, that's going to be a total of 60. And in 15, you're in this button over here has no mass, or I'm sorry, it has mass of 10. It has no velocity, so its overall momentum that it carries is now 0. It carries no momentum. It's not moving. It's simply just not moving. But this blue button over here, though, is moving. We just don't know how fast it's moving. So we rewrite it as 15 mass times v, okay? And then we simply solve for v. How would we do that? We would divide both sides by 15, the algebra way, to get rid of the 15, and we'll have it just say v. So if we divide this side by 15 and this side by 15, this is going to cancel out. The 15s will not be there. But 60 times 15, especially if you're like really well acquainted with clocks, because we have 60 minutes in an hour, quarter of an hour is 50 minutes, or whatever. I don't know. Maybe you don't remember all that stuff, but 60 divided by 15 is 4. So the velocity of this button over here is now traveling at 4. If you don't know the units, it's just meters per second. So let's get a little bit more cray. Okay. So again, pause at any time. I'm just going to do like 2 more slides of calculations for you. Okay. Okay. 2 cars before. So obviously you guys, this can get a lot more insane, but we like to just keep our examples really simple for the concept of momentum. It's just typically we're looking at one thing that's moving or sitting still, getting hit by something else that's moving, and then seeing what their momentums are before and after. So same case over here, two automobiles. One is a big truck, one is a car. So the thing that I want you to focus on is the first, the upper before part, okay, right before. This truck has a momentum of 1,000 kilograms. That's a lot, and it's going at a speed of 5 meters per second to the right. Okay. Now this little zippy car is only 800 kilograms, and it's not going quite as fast. In fact, this truck is actually really mean. Like, this guy should just slow down. He carries too much momentum because he's got such a high mass. Okay. This guy's already traveling kind of fast, but not fast enough. 800 kilograms and 2 meters per second. Let's calculate the momentum, which they did right here. It's 800 kilograms times 2 meters per second. A total, that 800 times 2 is 1600 right here, or 1600. And then the unit is kg times ms, which is kilograms meters per second. Okay, so that's its momentum. Wonder what this momentum is. How would we do that? How would we do the momentum for that guy? It would be 1000 kilograms times 5 meters per second. So do that in your head. 1000 times 5, that should be, the momentum should be 5000 kg times ms. Okay, so they're both heading towards the right. Okay, so this is before they hit. Then they hit, and now look at the new, oh, I should have covered this up. The new momentum, okay, the new speed. This guy slowed down. So it looks like this car slowed down when it hit after the collision, okay? Because he's probably like, oh, crud. Okay, I'm just kidding. It has nothing to do with the emotion. It's simply, after that truck hits, it's going to slow down. It transfers some of its momentum into this car, okay? Some of its velocity into this car. Okay, so check this guy out. The mass is still the same, 1000, but its new speed is 3.4 meters per second. So 1,000 times 3.4 meters per second. Yeah, you can see the math done here, but it's 3,400 kilograms meters per second. The new car, not the new car, it's still the same car as up here. I'm going to highlight it up here. Okay. This car over here had a mass of 800 kilograms. And guess what? After the collision, it still has a mass of 800 kilograms. But look at the new speed. It's faster. It's 4 meters per second now, and it's 2 meters per second up here. Let's see if what their momentums will be and if momentum was conserved. Okay, that's 4 meters per second. So it's 800 kilograms times 4 meters per second. Sorry, I'll put my face back in the picture. Hello. Hello. Did you miss me? Okay. 800 kilograms times 4 meters per second. 800 times 4, that's 3,200. And that's 3,200 kilograms times meters per second. Let's see if momentum was conserved. Okay, so let's put me back in, coach. Okay. So let's just double check really quick. Here is the truck before. Okay. Here's this little zippy car before. Okay. Okay, so before the momentum was 5,000 kilograms meters per second, or times meters per second, and over here was what, 1,600 kilograms meters per second. Then it became this, and like, you know, it was about to hit, then okay, then you get this. Now this kind of slowed down, but this car is going way faster now, right? And now its new momentum was what? It was 3,200, or no, let me see what it was. Its new momentum was 3,400 kilograms meters per second times meters per second, like that. Oh, sorry, I wrote my units wrong. It's kilograms times meters per second, and this is kilograms times meters per second. And this one down here was kilograms times meters per second. You have to get it right, okay? And then this one over here that we calculated was 3,200 kilograms times meters per second. In order to check, just add these up to see if they will be the same on the before and the after. Let's see if all the calculations were done right. Just add 5,000 plus 1,600. That'd be 6,600 kilograms meters per second total momentum on the before. And if we did the calculations right, it's 3,400 plus 3,200. If you add those together, yep, that is 66 kilograms times meters per second. Okay, so that means momentum was conserved as it should be. Okay, momentum was conserved as it should be. As physics gets more complex, you'll learn that momentum should always be conserved, but you might lose it to like the ground and friction and all these other arrows and all this other stuff. This is what makes physics really complicated. But we're just saying in a perfect world, two objects, all the momentum goes from one guy, and maybe part of it comes out the other, and it's perfectly conserved. Okay, but in actual real life, there's other things you have to take into account. But for the most part, it's one car's momentum gets, you know, like it loses some of its momentum or velocity, and the other car gets it perfectly. But sometimes it's like one car hits and it loses a lot of velocity, and the other car doesn't get quite all the velocity as it should, but it goes somewhere else and like forces and whatnot. Okay, it gets really complicated, but this is keeping it simple. And I'm sorry if it's like really tough and it's like, this isn't simple, Mr. Wei. I actually want to hit you, Mr. Wei. Okay, so you can turn the video off at this point if you think you've had enough, but I'm going to go through one more example just so you feel a little bit more comfortable with momentum, because this is like the only lecture I think this week. I think depending on what year this is, like I might assign this chapter with another chapter, but for the year that I'm currently recording right now, for you lucky folks, this is the only chapter that we have left this month to discuss. Okay, so let's check this out. Oh, another case. We have a cargo truck or train coming this way. It has a mass. What mass? Let's check out what it says on the left hand side. Consider a 42,000 kilogram train. Oh, it's traveling at 10 meters per second towards another train. So this must be the train that they're talking about here, okay? And it's coming and it's going to hit this. Oh, wow, that's really scary. A train that seems to be carrying like a container of like some kind of liquid. Hopefully it's not gas, okay? It has a mysterious mass, because look, I don't see the mass anywhere, do you? Written in here? Well, I've looked at this slide a little bit further before you did, but look. Oh cruddy, I do not see a mass for this. So it looks like that's the question. What is the mass of the second car train? Oh my god, it's the question, okay? Not to be insulting your intelligence or anything. It's just I'm talking that way because it's not actually surprising me, because I wrote the freaking slide, right? Or I grabbed it from the internet, okay? So after the collision, they couple together. So check it out. They collide and they actually couple together and they both move at the same speed. Notice that the first car was traveling much faster before the collision and it lost some of its speed, but now the other car shares that speed, okay? We're going to use all these details to find the mass of that train, okay? How are we going to do it, Mr. Wee? Okay? You don't have to keep drawing it like I do, all right? But I like to draw it, so I like to say train before is about to hit this guy, and then I'll do the after side. So I could do before and after. You don't have to do it this way. I'm showing it many different ways and calculating whatever makes more sense to you. And then afterwards, they like I'll put at the line they like actually collide, right? Like on the actual line, like the dividing line, I'll actually say is the moment of impact. Like psh, they hit, but then now after is both of them are moving. So they're both moving. And they're both moving at 6 meters per second and 6 meters per second. Over here, this guy was actually moving 10 meters per second, and he was 42,000 kilograms. And this guy is still 42,000 kilograms, so that's really nice to know that. I don't know the mass of this guy, but I do know the velocity. The velocity of this guy is equal to 0 meters per second. It was standing still, wasn't it? Okay. So let's break down what I got. Let's take inventory of what I have. Let's call this A and B, and let's call this A after and B after, okay? So I want to calculate the momentum of A. So the momentum of A is equal to mass of A times velocity A. And that would be 42,000 kilograms times 10 meters per second, which will be, holy crap, 420,000 kilograms meters per second. Okay, so that's what I should have. But don't forget to do that for B. P of B will be mass of B times velocity of B. Its mass, I don't know. But you know what? Does it really matter on the left-hand side on this part? Look, its velocity for sure is 0 meters per second. What's anything times 0? It's just 0. So who cares? It's just 0. If I really care about the units, it's 0 kilograms meters per second. And then the whole point is you have to add the momentums together on this side, which would be 420,000 kilograms meters per second plus 0 kilograms meters per second. Oops, not meters per second squared, just meters per second, which give me a total of 420,000 what is it? Kilograms meters per second. Okay, so here's what I was gonna say. That I'm gonna say that PA is equal to plus PB, the total momentum on this side, has to equal the total momentum on this side. Whoops. Oh, like that. The momentum of A after plus the momentum of B after. Okay. So we're gonna expect that if this side is 420,000 total momentum, this side has to be 420,000 total momentum, okay? So let's break down some things here. PA prime, or the momentum of this after, is actually going to be 42,000 kilograms. Oh, whoops. Or actually, I'll write the variable. So remember, we do M of A, and I could say prime like after, but the mass is just the same. So I can just leave it as MA times the new velocity of A, which in this case is 6 meters per second. And then PB prime is going to be the mass of B, which I really don't know still, times the new velocity of B, the prime B. So let's plug in some stuff. So that's 42,000 kilograms times 6 meters per second. That's going to be a little bit different. 42,000 times 6 is actually less. So I don't know if you guys can see this, but whoops. Okay, give me a sec. Sorry. Got some personal stuff on here, slightly personal stuff. Okay, so it's 42,000 times 6. That's 252,000. So it's a little bit less than it was. So remember what its momentum was before, 420,000. Now it's 252,000. You're like, oh, look, that much less to me. No, that's a lot less momentum. Over here, however, we don't know it. We don't know it. Okay. Over here would be it's still, the mass is still unknown, but we do know the velocity. The velocity is now 6 meters per second. Okay. So the total thing is MB. You can't get more simpler than that. Like, you can't simplify that any more than that. Okay. So this is the new scenario that we have. This is equal to this, 252,000 kg ms plus mb times 6 meters per second. Sorry, 6 meters per second. Okay. You know what? I know that the total will be 420,000 on this side. Okay. But you know what? I'm going to make room to continue work down here. This is what's new. So this is where I'm going to do some math here, and I'm going to set that equal to, because 420,000 plus 0 gave me this. This has to equal 420,000 as well, but I'm just going to carry this down instead. So that's 252,000 kg ms plus mb times 6 ms. Okay? Or kg ms. So crap. Wait. Actually, no. I apologize. I'm wrong. Not to freak you out. You're like, what? This is already confusing enough as it is, Mr. Wade. Don't make my life a bigger living hell, okay? Okay, so what we're gonna do is we're gonna solve for m. Okay, what I want you to look at this, like, essentially, if you could, it's just 400. Without the units, it's just 420,000 is equal to 252,000. And instead of MB, let's just look at that as like an X. X times 6, or 6X. Do you see now? Do you see the math that we're about to do? Like, instead of MB, I'll put just an easier letter. So it'd be 6X. All you would have to do, if you remember your algebra, is subtract 252,000 from both sides. You should still have a number over here. That's going to be equal to 6X, and you divide both sides by 6. Okay? So don't write the next part if you're writing any of this right now. Like, if I subtracted 252,000 from both sides, what would that give me? That's 420,000. Dang it. So annoying. 422,000 minus 252,000. That's 168,000. That's 168,000 is equal to 6x. And let's say, and then after that, you just divide both sides by 6. That's 28,000 is equal to x. That's essentially what I'm going to do. All this stuff is what I'm going to do with these numbers. Just, it has units and stuff, okay? So let me back up. So our answer will be 28,000. I'm just showing you, like, how to look at it, what it should look like mentally, sort of, in your head. Give me 1 second. Sorry. Oh my god. Alright. This is getting quite annoying here. Okay. So here's what I'm going to do. Alright. Only I'm going to involve units now, because this is physics and I do have to show it to you in the physics way. So again, you would subtract 252,000, but let's add in the units of kg ms. And I subtract 252,000 again, but just add the fact that there's some units here, kg ms. So, oh, that doesn't exactly cross out, but what you should get, because it doesn't cancel out completely. 428,000 minus 252 is 168. Same thing as what we were just doing before, kgms. And then over here on this side is equal to, what we have left is like mb times 6ms meters per second. And just like before, just imagine that as 6 times x, or m in this case, and this is just this number, and we're going to divide both sides by 6 to get m by itself. Okay, so but instead of just 6, it's 6ms. So the whole thing cancels out. This and the units cancel out. Okay, and that's been happening the whole time. kgms minus kgms. Okay, like they kind of just cancel out. So this time when I divide this side by 6ms, I know it's kind of hard to believe, but ms over here will cancel out, because it's like saying kg times, and let's say ms is like a number, or x. Let's just say that is replaced with x. When you divide kg x divided by 6x, let's say ms is x here, the x's cancel out, right? Sorry, I'm using a lot of analogies here, but if you can follow along with what I'm saying, good. But if you can't, it's okay. Come and see me for tutoring, or let's make an appointment this year, since Mr. Weed's like a little bit busier. I'm out of whiteout. Okay. So ms will cancel out. 168,000 divided by 6 is 28,000. Now what's the remaining unit? Kg, that's kilograms, is equal to, what do I have over here? MB. That means the mass of B before or after, does not matter. The mass is equal to, does that make sense? 28,000 kg, is that the unit for mass? It is. It is. Yes, we do want a mass, 28,000 kilograms of mass. Okay, so if you were confused at all, rewind this, okay, like a bunch of times until you get it, okay? But the concept's not too bad, right? Once you get a rhythm for doing some of the problems and whatnot, you should understand it a lot better. But momentum, again, is just mass times velocity. Just remember the momentum before a collision and after the collision, the total has to be the same, okay? So that's really it. I just did some of the math for you to understand it even more at a higher level, but as long as you understand the basics. Okay, class, that's all I got. So I'll see you guys.